Hello everyone, welcome to the third video lesson for Chapter 3 of the Foundations of Scalable Systems. In the last lesson I talked about the basics of the TCP and UDP protocols. It's perfectly feasible to write our distributed applications using low-level APIs that interact directly with the transport layer protocols TCP and UDP. The most common approach is using the standardized sockets library. This is something you'll hopefully never have to do, as sockets are complex and error-prone. Essentially, sockets create a bidirectional pipe between two nodes that you can use to send streams of data. There are, luckily, much better ways to build distributed systems, as I'll describe in this lesson. These approaches abstract away much of the complexity of using sockets. However, sockets still lurk underneath, so some knowledge of how they work and break is necessary. Socket APIs that write directly to the transport layer are available in all mainstream programming languages, but regardless of the language, the sockets library is low level and it's hard to use. Let's use an example of how you might use sockets based on our mobile banking application. Here on the slide here, you see that a client might send a request to get their balance and specify their bank account. We'd have to encode this information as part of the data stream that we send over a socket. The server would then pull that data off the socket, interpret it as the request for a balance for a particular account. It would then execute a database access, get the results, and return a package to the clients based on this sort of format here, which specifies this is the account number and this is the paltry balance that you have in your account. In any complex system, the server will support many operations. In our banking example, these might be as shown on the slide here: a login, a transfer, change your address, get a statement, view transactions, etc., etc. Each of these would be followed by different message payloads that the server needs to interpret correctly to fulfill the client's request. What we're really defining here is an application-specific protocol. As long as we send from the client the necessary values in the correct order for each operation, the server will be able to respond correctly. If we have an erroneous client that doesn't adhere to our application protocol, well, our server needs to do thorough error checking and respond accordingly. The socket layer provides a primitive low-level method for client-server communications, but sockets are really efficient, but they make it difficult to correctly implement the application protocol to handle all possibilities. They're frail and not resilient to change. There are much better mechanisms. If we step back for a moment, what we're really doing is defining an interface similar to what we would do in an object-oriented programming language such as Java for our banking application. It would have a number of methods as shown on the slide here, and each method is passed an appropriate parameter and returns an appropriate type that satisfies the particular method's semantics. There are several advantages of having such an interface. For example, the interface is clearly defined by the class definition and thus straightforward for client programmers to understand and utilize. Calls from the client to the server can be statically checked by the compiler to ensure they're the correct format and argument types. This is a sort of thing that we have utilized and exploited in object-oriented systems for decades. The advantages of clearly defined interfaces were recognized reasonably early in the creation of distributed systems. Since the early 1990s, we've seen an evolution of technologies that enable us to define explicit server interfaces and call these across a network using essentially the same syntax as we would in a sequential program. A summary of these approaches is shown on the slide here. Collectively, they're known as remote procedure call or remote method invocation technologies. While the syntax and semantics of these RPC and RMI technologies vary, the essence of how each operates is pretty much the same. Let's continue with an example of the server interface to examine how this works in the Java remote method invocation approach for building client-server applications. Using Java RMI, we can trivially make our bank interface example as shown on the slide here. Basically, our interface is the same as Java, A normal Java interface, except it extends the remote interface. This basically tells Java that we're creating a server that can be called remotely across the network. In addition, each method returns a remote exception, can throw a remote exception. Remote exceptions can occur when there's a network failure between the client and the server, or the server has crashed and is unavailable. To instantiate our server object, we must provide a class that implements our interface, as you can see on the slide here. The basic ingredients of this are shown on the slide. Basically, we extend the unicast remote object, which basically specifies that this object should be remotely callable across the network. Next, we construct the object and we store a reference to the object in a system entity called a registry. A registry basically is a directory service which clients can use to locate servers. Here we're creating a registry entry of the name IG server, and we're storing it in the reference to the server associated with this logical name in the service. Now servers can look up our logical name and obtain a remote reference to our server by querying the registry. This example shows an extract from a client which makes a call to our bank server. You can see here that to get a reference to the server, a remote reference, it performs a lookup operation to the registry for the logical name. The returned remote reference is then used to call the balance method associated with the bank server's interface. This slide shows how all the components of an RMI system fit together. As you can see, the stub and the skeleton objects here are basically generated by the Java compiler based on the RMI interface definition, and their aim is to facilitate the actual remote communications between the client and the server. The skeleton here is in fact a TCP network endpoint, basically the host and port number that listens for calls to the associated server object. When we deploy our server, you can see the sequence of operations that occurs here to make a call. First of all, the server is deployed. It stores a reference to itself in the registry, its logical name, and it deploys its skeleton, which can listen for requests from clients. Next, the client will make a call to the registry, and what is returned is the actual stub that can be used to make calls to the server object. Next, the client will actually make a call to the returned reference. This will actually be passed to the stub object, which will then make a TCP call across the network. The skeleton will intercept this, process it, pass it to your bank server. It will then invoke the method that implements the method that's being called in the interface. The results are then returned to the skeleton, which then returns or marshals the results back to the stub, which passes these back to the client. Even though this is Java RMI, essentially all RPC RMI mechanisms work exactly the same. The basic attraction of these RPC and RMI approaches is that they provide an abstract calling mechanism that supports location transparency for clients making calls to remote servers. Location transparency is provided by the directory service. That means it's possible for the server to update its network location in the directory without affecting the client's implementation. These RMI and RPC approaches are not without flaws, however. The marshalling and unmarshalling of objects across the network can become inefficient for complex object parameters. Cross-language marshalling, clients in one language, server in another, can cause problems due to data types being represented differently in different languages, causing subtle incompatibilities. And if a remote method signature changes, all clients need to obtain a new compatible stub, which can be cumbersome in large deployments. For these reasons, most modern systems are built around simpler protocols based on HTTP and use JSON or XML for parameter representation. Instead of operation names, HTTP verbs such as put, get, post, etc. have associated semantics that are mapped to a specific URL. This approach originated in the work by Roy Fielding on the REST approach. REST has a set of semantics that comprise a RESTful architectural style, and in reality most systems do not adhere to these semantics. I'll discuss REST and HTTP APIs in subsequent lessons. Well, that's it for RPC and RMI approaches to building distributed systems. While not prominent in the industry now, I'm sure many of you will bump into them in many of the systems that have been built over the years. In the next lesson, and the final lesson for this chapter, I'm going to explain some of the fundamental issues that all distributed systems are constrained by. Understanding these is crucial to be able to build scalable and available software systems. Thanks for watching.